Welcome. Among all the geometric structures, topological structures, the metric spaces are the champions. It's the most important structure which you see in a topological framework. Manifolds, for example, are usually assumed to be metric spaces. Riemannian manifolds, for example. Among all algebraic structures, groups are probably the most prominent ones. It's not the most general, but they are the most important ones. And you can ask, and that's what I did in 2008, I asked myself, is there some connection there? Can you get metric spaces such that the algebraic structure is determined by the metric? Or does space define time? And so here is the definition. That's actually the correct definition which I used in the paper, and I overstated the definition, and I will come to that. It's kind of an example to this epistemology story of Lakatos about proofs and refutations. So this is the correct definition. With a different definition you get different results. And I'm grateful to Jakub Gismatullin to point that out. So he has another definition which gives different results. But let's just start from the beginning. So we have a set X with a metric structure, and we call this metric space natural if there exists exactly, up to isomorphism, one group structure on X such that right translations are isometries. Strongly natural would mean that we have both left and right translation to be isometries. I stated that in that paper of 2022, but it's actually what I used is right translation. So this is the definition of natural. Call this now, and that's Jakub has calls this strongly natural. Now the corresponding group which you get then is what we can call a natural group. And example of a natural group is the cyclic group Cp for prime P. So first of all there is a metric space which is the cyclic graph with P elements. It's one between neighboring points. You take the cyclic graph, and what happens is there is just one group, because there is only one group structure. That follows from Lagrange theorem in group theory. There is no other subgroup because of the prime condition. An example which is not natural is K4, very special. K4 is K4, that's as a metric space. This is not natural because it has two groups which act as isometries, and because on a set with 4 elements you have only abelian groups, there the difference between strongly natural and natural, there's no difference between strongly natural and natural, and so the results are then the same. But the results already get different when you look at Z. And that's something which I learned from Jakub Gismatullin, which I kind of missed. So for me, with the notion of natural, Z is not natural. And the reason is because there are two group structures which are both acting as right translations, as isometries, and one of them is abelian, the other one is not abelian, so they are different structures. And so here is the kind of the situation, the labeling of this group. You know, you have you have the metric is right invariant, right? If you take the distance between B and AB here, that's the same as the distance between 1 and A. But, and that's what I missed, it's not left invariant. If you look at the left, it's not left invariant. If you look at the distance between A and AB, right, A and AB, that distance is equal to 3, while the distance between 1 and B is equal to 1. So you cannot impose both left and right invariance, and so this group, the infinity, doesn't admit any metric, which kind of forces it with a strong naturality condition. With a naturality condition here, you only want a one-sided translation invariant, then you have a unique group structure here. By just, what you can do is you can just break the symmetry here. You take the metric and you, instead of doing the equal distance, which then also would allow Z, you just break the symmetry. You take the distance 1, 2, 1, 2, and so on. And then in that case, the group action is still isometry. So what happens here, you can take as the generators, just the reflections at the center here and the center here. These are two reflections which generate the group. And what happens if you take the composition, then you get the translation. So you get the translation, which is isometry. So you have here D infinity is natural, Z is not natural, but D infinity is not strongly natural, and D infinity and Z is strongly natural. And this reflects in other cases, like the dihedral group. There is also a switch like this. There are other cases, like here, where the results are the same. And that's it for today.